Since we now know of the relation between luminosity and mass, even when we can't use Kepler's third law and we don't have a binary of stars, we can actually estimate how much mass there is in a star. And this is crucial because it tells us about the amount of fuel available to be converted. This amount of fuel is hard to determine how long the star can actually live for, especially in this longest period that we call the main sequence. During the main sequence lifetime, what the star is doing is essentially converting hydrogen into helium. In practice, what happens in stars is that about 0.7% of the hydrogen mass will be lost in the fusion process. In other words, it will be converted into energy. Those 0.7% that are lost when an hydrogen nuclei becomes an helium nuclei will be lost to this energy, and this energy then actually radiates. This is what actually powers a main sequence star. We'll not be discussing this in full detail, and you'll find an in-depth discussion if you do Physics 264, but it is good to have an idea that about 10% of the total hydrogen mass can be burned or transformed into helium before the star actually becomes unstable. This also means that the stars do not transform all their hydrogen into helium. 90% of it will actually be left over before the star will then start to burn helium and sometimes even oxygen and carbon later on if it is hot and massive enough. Now, if we want to calculate what we call the main sequence lifetime, how long the star will be stable while it's burning hydrogen, what we actually need is to look at the ratio between the available energy and the average luminosity. What we're basically saying is that the main sequence lifetime will depend essentially on the ratio of the total amount of energy available, which will be given by hydrogen, which will essentially be given by how massive the star is, divided by its luminosity. If a star is much more luminous, it means it is burning the fuel quicker and therefore will last for a much shorter amount of time. In practice and with simple arguments, what you can say is the main sequence lifetime should be proportional to the fuel divided by luminosity, because the fuel is essentially the mass of the star. Then you can write that this is the mass of the star divided by the luminosity. And because we've seen that luminosity goes as m to the power of 4, we can actually rewrite L as m to the power of 4 to realize that the main sequence lifetime is proportional to 1 over the mass of the star to the power of 3, or in other words, proportional to m to the power of minus 3. This may be surprising to some because you'd think that a star with more fuel will last for longer, but the problem is a star with actually more fuel becomes so much more luminous that the effect is actually contrary, and therefore the more fuel a star starts with, the shorter its main sequence lifetime because of how luminous those stars will be. The Sun, for example, is expected to have a lifetime of something like 10 to the 10 years or 10 gigayears, and therefore in solar units we can say that the main sequence lifetime for the Sun is 10 gigayears. And this becomes really interesting because once we know the lifetime of the Sun, we can actually write an equation to calculate the main sequence lifetime from any star, provided that we have measured the stellar mass in solar units for that specific star, which, as we've seen, can actually be obtained by measuring its luminosity. So you can really see the full extent of our astrophysics superpowers in now even determining how long a star will live for before it actually goes off the main sequence, and as we'll see in the next section, essentially end up as a white dwarf, a neutron star, or a supernova. The final important thing to point out in terms of main sequence lifetime is that because of the scaling, the most massive stars are the ones that have the shortest main sequence lifetimes, sometimes of only a few million years, while the stars with the least amount of mass can actually live for longer than the age of the universe. And also that mass really is critical, not only for the production of luminosity, but ultimately the critical predictor for how long a star will stay on the main sequence. You'll cover these aspects in a quantitative way if you do 264. For 263, the important thing to realize is that stars remain on the main sequence because of this equilibrium between gravity wanting to crush them and radiation pressure pushing it back, and also that sometimes, and specifically for the very massive stars, there are processes that lead to a boost in energy, and therefore you can get things like winds or stellar winds. And also, when hydrogen runs out and you start burning heavier elements, this equilibrium is very unstable, and there are stars that end up just contracting and then expanding all the time for a periodic amount of time. Of course, because fuel is not infinite, then radiation pressure always loses given enough time. But also it is important to understand that in order to achieve this equilibrium, mass is the primary driver. And that essentially the class of the star, the size of the star, the temperature, the color, the lifetime, even the luminosity, all are essentially a consequence of the mass radiation equilibrium condition. It also means that if you measure the mass of the star, then you can actually predict all the other physical properties of a star. This is the end of section 8, where we talked about stars and specifically main sequence stars. I hope you've learned a lot about how we classify stars and how that system came about, how stars from O to M establish a sequence in temperature, in size, luminosity, and even in mass, and how mass is fundamentally the most important predictor of all properties of a main sequence star. As always, I would encourage you to go through the lecture notes, get in touch if you have any questions, and also try to attempt the questions at the end. That's section 8.8. If you do all of that, then you're definitely ready for section 9, where we're going to be talking about the processes before the main sequence, essentially how stars form, and also after the main sequence, or how stars die. So I'll see you for section 9.